Good morning. We are going to discuss numerical examples of forced vibration of single degree of freedom system. We have derived the expressions for response of system with damping, system without damping, and based on that derivation, some simple examples will be dealt with now. Question number 1. A single degree of freedom system with mass 100 kg and stiffness 15 kN per meter is subjected to a harmonic load 120 cos 18 t Newton. Assume 3% damping. Compute the amplitude of steady state response. We will deal with this. The first question. The given data are mass of the system is 100 kg. Stiffness of the system is 15 kN per meter. Harmonic load, the load is, we usually write F0 cos omega t. The external load or the exciting force is given as 120 cos 18 t Newton. And the damping is 3%, so damping ratio is 3 by 100, 0.03. So this is damping ratio. These are the given data. We are asked to find out the amplitude of steady state response. Amplitude of steady state response. That means the dynamic displacement. We have derived the expression. The magnification factor. Magnification factor is nothing but the dynamic displacement. Say x dynamic to x static. The ratio of dynamic displacement to static displacement is called magnification factor. And the magnification factor is 1 by this expression we have to remember 1 minus beta square the whole square plus 2 psi beta the whole square. This is the expression for magnification factor. Now, the steady state amplitude is nothing but the dynamic response. We have to calculate x dynamic. So, that will be x static into mu. So, let us calculate this first. What is the magnification factor? For that, beta is nothing but the frequency ratio. Frequency ratio is the ratio of the frequency of the exciting force, capital omega, to the natural frequency of the system, omega n. Frequency of the exciting force to the natural frequency of the system. Frequency of the exciting force is given in the question, 18. Referring to this, ohm is 18. What about omega n? The natural frequency, omega is equal to root of k by m. Then the k of the system is given 15 kN per meter. So 15 into 10 raised to 3 Newton per meter divided by mass of the system is given 100. So root k by m will give you the value 12.247 radian per second. So you can calculate beta. Beta is equal to ohm by omega. 12.247. Beta will work out to 1.47. So substituting in this expression, we have the value of beta, we have value of psi. So this will be 1 by root of 1 minus beta square, the whole square, plus 2 psi, 0.03, beta, 1.47, the whole square. It will work out to the magnification factor is 0.8588. Now what is static displacement? Static displacement is force divided by stiffness, F0 by K. So F0 is 120 divided by K, 15 into 10 raised to 3. So the static displacement is 8 into 10 raised to minus 3 meter, or it is 8 millimeter. Therefore, the dynamic displacement of steady state amplitude, X dynamic of the steady state amplitude of steady state response is equal to mu times X static. So that is equal to 0.8588 into H will work out to 6.87 millimeter. It's a very simple example directly based on the formula. Static displacement, ratio of dynamic displacement to static displacement. The maximum dynamic displacement, X max, to X static is called the magnification factor, which depends upon the frequency ratio as well as the damping ratio of the system. Question number 2. The displacement amplitude of a single degree of freedom system due to harmonic force is known for two excitation frequencies. At ohm is equal to omega n, it is 5 millimeter, and at ohm is equal to 5 omega n, it is 0.02 millimeter. Estimate the damping ratio of the system. Okay, question 2. Let us see what are the data given to us. In case 1, when ohm is equal to omega n, that is the natural frequency of the system is equal to the excitation frequency. What is the frequency ratio? The frequency ratio is ohm by omega n. So in this case it will become 1. That is corresponding to resonance condition. We are given the amplitude is 5 millimeter. Okay. Second case is at ohm is equal to 5 omega n. So what is beta? Beta is equal to 5 omega n by omega n is equal to 5. And the frequency ratio is 5. The value of the amplitude is 0.02 millimeter. These are the two values given in the question. Corresponding to frequency ratio is equal to 1, which is 5. And corresponding to frequency ratio is equal to 5, the displacement is 0.02 millimeter. We are asked to find out the damping ratio of the system. So we have the equation, we know the maximum displacement, the dynamic displacement X is equal to F0 by K, the static displacement into amplification factor or magnification factor, 1 minus beta square the whole square plus 2 psi beta the whole square. This is the expression we have derived earlier. The dynamic displacement or the maximum displacement is equal to the static displacement times the magnification factor. So substituting here the first case, 5 is equal to F0 by K into 1 by here 1 minus beta square the whole square. So beta is equal to 1, this term gets vanished. It will become 2 psi. Root of 2 psi square. So 1 F0 by K into 1 by 2 psi. Equation 1. For the second case, we substitute 0.02 is equal to F0 by K into 1 by root of 1 minus beta square the whole square plus 2 psi beta the whole square. This is expression 2. So 1 by 2, we divide 1 by 2 and square it. Divide 1 by 2 and take the square of it. So that we will get 5 by 0.02 the whole square is equal to, these two gets cancelled. This will go to the numerator. 1 minus 25, 24 square plus 2 into 5, 10. 10 square of 10 is 100. 100 psi square divided by 2 psi the whole square is 4 psi square. So you solve this equation and we'll get psi is equal to 0.048. You're asked to find out the damping ratio of the system. So the damping ratio is 0.048. Simply based on this equation, the magnification factor expression, if you know, you can do all the examples in this force vibration. So next question number 3. A steel frame supports a rotating machine which exerts a horizontal force at the girder level 50 into 10 raised to 3 sine 10 t Newton. Assume 4% critical damping. Determine steady state amplitude of vibration. Moment of inertia for columns 150 into 10 raised to minus 6 meter raised to 4. Young's modulus E 210 GPa and mass 5000 kilogram. So let us see what are the given data for question number 3. A steel frame. A steel frame. Bottom is hinged. This is the figure. This, suppose this is subjected to a load PT. There's a rotating machine based on this beam. This column height is given as 3 meter. And the force P is given as, the exciting force P is equal to 50 into 10 raised to 3 sine 10 T, exciting force. Damping ratio, critical 4%, so that is 0.04. And moment of inertia of columns 150 into 10 raised to minus 6 meter raised to 4. Young's modulus 210 GPa. Stiffness of mass of 5000 kilogram. Steady state amplitude. You are asked to find out the steady state amplitude. These are the given data and you are asked to find out the steady state amplitude. So what is the steady state amplitude? We have now discussed several times. The steady state amplitude is equal to F0 by K, the static displacement, into magnification factor, root of 1 minus beta square, the whole square, plus 2 psi beta, the whole square. That's all. See what are the terms are given, how to find all the remaining terms. So in the question, F0, that is given, 50 into 10 raised to 3. To find beta, the frequency ratio, beta is equal to ohm by omega. So for that, we have to get the natural frequency of the system. How will you find the natural frequency? Omega is equal to root of K by M. So you have to find out the stiffness of these columns. Mass is given 5000 kilogram. What about the stiffness? Both ends are hinged. The bottom end of the column is hinged. So stiffness of column K for the column. There are 2 columns. For one column, it is 3EI by L cube. If the bottom is fixed, it will be 12EI by L cube. Since the bottom is hinged, it is 3EI by L cube. So EI and length, everything is given. Substituting the values, you will get the stiffness as 7 into 10 raised to 6 Newton per meter. So we can calculate omega root of 7 into 10 raised to 6 divided by the mass 5000 will work out to 37.42 radian per second. So we got the natural frequency. So we can get beta. We can get the frequency ratio beta is equal to ohm by omega. Ohm is 10 and omega is 37.42. So the value of beta is 0.2673. Everything is given in the question. You can just substitute in this expression. X max for the dynamic displacement is equal to F0 50 into 10 raised to 3 by K 7 into 10 raised to 6 F0 by K into 1 by square root 1 minus beta square the whole square plus 2 psi. Psi is 0.04 beta 2 psi beta the whole square. So this will work out to 7.69 millimeter. So all the three examples which we have discussed now is based on this only one expression. The static displacement times the amplification factor or the magnification factor will be the dynamic displacement or the steady state amplitude. Coming to question number 4. The system shown in figure has K is equal to 40 Newton per centimeter, W 100 Newton, when the excitation force Ft is equal to 20 sine 10 t. Determine the equation of resulting motion. Question number 4. Given the figure like this. A stiffness. In the question, stiffness is given as 40 Newton per centimeter. The weight is given as 100 Newton. So I can calculate the mass is equal to W by G and D by 9.8 kilogram. So that these two will give me the natural frequency of the system. Omega is equal to root of K by M. Substituting root of 40 Newton per centimeter. So 40 into 10 square Newton per meter divided by 100 by 9.8 will give the natural frequency as 19.81 radian per second. Then the exciting force is 20 sine 10 t Newton. So this is P0 or the initial force. The frequency of exciting source is 10 radian per second. You can get the frequency ratio beta is equal to ohm by omega n. So it is equal to 10 by 19.81. It works out to 0.5047. And in this question, there is no damping, no mention about damping. So damping is not mentioned. Therefore, it is undamped force vibration. Since no data regarding damping is given, we can assume that it is undamped force vibration. For undamped force vibration, the response at any time, we are asked to find out the response or the resulting equation of motion is asked to be obtained. xt is equal to f0 by k into 1 by 1 minus beta square. In case there is no damping, the magnification factor can be taken as 1 by 1 minus beta square into sin omega t minus beta sin omega t. This is the expression for an undamped forced vibration. We refer back to the derivation and we can write here xt is equal to f0 20 by k. K is 40 into 10 square into 1 by 1 minus beta square. 1 minus 0.5047 square into sin 10t minus 0.5047 sin, the natural frequency is 19.81. So this is the expression for resulting motion, and this calculation, once you do this calculation, this will work out to 0.671. So this is the equation of response for an undamped forced vibration. So with that, we have covered all the numerical examples in forced vibration of single degree of freedom system. With that, we come to the end of that chapter, Structural Dynamics, Module 6. Thank you.